So for the first problem, it's asking which of the following functions represents y as a function of x. And so what that means is that to be a function, y to be a function of x, we need that each x input has a unique output. And so if I look at this first problem here on part I can see that I have the input 2 has the output 5, the input 1 has the output 6, the input 3 has output 7, but look here, input 2 has output 8. So I see that 2 having two different outputs. And so this one is not a function. Okay, because we have an input that has two different outputs, so it doesn't have a unique output. The second one, I look at the inputs, 5 to 2, 6 to 1, 7 to 3, 8 to 2. Each of those inputs has a unique output, so this one is a function. If I look at number 3, I'm seeing like for each individual x, so I'm looking at each x input and I want to see the outputs that go with it. So I see for this x input I have two outputs. And so I can think of this as like a vertical line. So for some x output, I hit the graph at two different places. So this one is not a function. Okay, and then this graph of this parabola looking graph here, I can see that for each x input, I have a unique output. In other words, I hit the graph at one spot. And so this one is a function. So for the second problem, I am looking at a table that for a certain date gives the population of the United States in millions. So the first question says, what is the average rate of change in the U.S. population from 1990 to 2000? And so if I want to find an average rate of change, I'm going to compute a change in population over a change in time. And so I'm looking for the years from 1990 to 2000. So I'm going to look here in the table. And I can see that the population goes up from 291 million to 281 million. So my rate of change should be a positive number because I can see that the population is going up. And so I can do 281 minus 249 to find out how much it grew over, and I can do 2000 minus 1990 to find out the change in years. And if I go ahead and compute that, in my calculator here, I get 3.2. And let's think about what the meaning of that 3.2 is. Well, first of all, we can think about units. And so if I look back here, I can see that I computed this by doing the change in population over the change in time. And so what are the units of population? Well, population is measured in millions of people, and time is measured in years. So the units of this are million people per year. Million people per year. So what that means is that in that time frame from 1990 to 2000, the population was growing at approximately 3.2 million people each year. Okay, and then it says, what was the average rate of change from 2000 to 2010? So now I'm going to be looking here at these 2 years, And so I can see I again want to do the change in population over the change in time. And so I can compute that. I can see that the population rose from 281 to 309, so I should expect that my average rate of change will be positive. And so I can compute this average rate of change by computing the change in population, 309 minus 281, over 2010 minus 2000. And when I compute that, I get 2.8. And again, the units of that are going to be the units of the top per units of the bottom. And I see that the top is measured in million people per year, million people, and the bottom is measured in year. So the units of the 2.8 are million people per year. Okay, the next problem says I want to find the intervals on which the function is increasing or decreasing. So what increasing means graphically is that the function is going up as I move from left to right. So I'm going to start at the left-hand side of my graph, and I'm going to see what it's doing. It looks like here it's going up, it's increasing, and then at some point here it reaches a maximum, and then it's going to be decreasing there until it reaches this minimum, and then it's increasing again. And so when it asks here the intervals on which the function is increasing, what that means is intervals of x values. So we need to look at the values of x when the function is increasing and the values of x when the function is decreasing. So if I want to find the values of x that the function is increasing on, it looks like it's increasing when x is less than -3, and it's also increasing when x is greater than -1. So we can write that down in interval notation by saying if we want to say all the x values less than -3, I can say for x in this interval from -infinity to -3. And I can also say I also have the interval from -1 to infinity. So I'm going to say union -1 to infinity. And it's decreasing for all x values in the interval from -3 to -1. Okay, and here I'm going to look at the function shown. I want to find what interval the average rate of change is the greatest and why. So what I'm looking for here is the average rate of change graphically means that I'm looking at the slope. And so if I look at the slope from the point where x is -7 to where x is -5, I can see that slope looks pretty close to 0. Then I can look at the slope from, I'm going to use a different color here, -5 to -2. It looks like maybe slightly steeper, but still not very steep. We have a kind of a slightly positive slope. And then if I go from -2 to 1, that would be here, I can see I have a steeper positive slope, so this seems like the slope is increasing. Then I look again from 1 to 2, and so that looks like the steepest one. And since they're all positive slopes, the steepest one will be the greatest. And so this one will have the steepest slope. Which is also positive. So that means it's the greatest. And that's a slope of, I guess we can call that a secant line. Is the greatest. Okay, so the next one, I have this function that tells me when water, or a table that tells me the temperature at which water boils. It's depending on the altitude above sea level. So the first question asks, is the data in the table linear? And so to answer that question, I want to look at the average rate of change for each of these intervals. And so I'm going to start with the interval from 1.1 to 2.2, and I can compute the average rate of change. I can do 208 minus 210 over 2.2 minus 1.1, and I get the average rate of change is negative 2 over 1.1, whatever that is. If I compute the next interval, I can get, maybe I'll do that in a different color so you can kind of see what I'm doing here. If I compute that one, I can do 206 minus 208 over 3.3 minus 2.2, and I get negative 2 over 1.1. And then if I do this one, I get 204 minus 206. Looks like it's a change of 2, and then a change in the in the altitude of 1.1. So 4.4 minus 3.3 gives us again negative 2 over 1.1. And so since we have the same rate of change, so the data is linear, yes. And we can say the average rate of change is the same for each interval. Okay. And then it says, use the formula to express the temperature T as a function of the altitude A. And so what I've computed over here is I've computed my slope. So I have already computed my slope. And so the thing I don't know is my kind of like my initial value, or in other words, the temperature at which water boils when the altitude is 0. I don't know that value yet. But I can I can write down a linear function. We know that linear functions are often expressed y equals mx plus b, where m is the slope and b is the value of y when x is 0, or in other words, that's our y-intercept. And so here I'm going to use that same formula, but I'm going to use the variables that I'm given. So I can write t is equal to ma plus b. And so I know my m is negative 2 over 1.1. So then I can plug in that m, and I can plug in an a and a t, and so I get, we'll see, 210 equals negative 2 over 1.1, and I'll use the a value of 1.1 plus b, and I can solve for that b. And so I end up getting 210 is equal to negative 2 plus b. In other words, I can add that 2 over, I get b is equal to 212. And so that means our function then is t is equal to negative 2 over 1.1 a plus 212. And so the slope of the function is negative 2 over 1.1, or in other words, I can get a decimal approximation of that. So the slope is negative 1.0. It's repeating 8181. And the units of that are going to be degrees Fahrenheit per 1,000 feet. And that means for each 1,000 feet, the temperature, the boiling point of water, decreases by negative 1.81 degrees Fahrenheit. So maybe I won't even say SO. It decreases by that, so I'm not going to say it decreases by negative. That'd be a double negative, so I won't do that. Okay, at what temperature does the water boil in still water, which has an altitude of about 900 feet? So 900 feet is equal to 0.9 1,000 feet. Remember, our units are in thousands of feet. So then our input A is going to be 0.9. So we'll do T of 0.9. I want to find the temperature when the altitude is 0.9 thousand feet. And I get, I'll use my function, negative 2 over 1.1 times 0.9 plus 212. And if I compute that, I get 210.363. And that is a temperature, so degrees Fahrenheit, the units of that. So here I want to find the equation of the line that passes through this parabola. That's the parabola. Y equals negative 1/2 x. So that's a parabola. Y equals negative 1/2 x minus 2 squared plus 1. That's the parabola there. And then I want to do that at x equal 2 and x equal 4. So maybe I'll erase that. So at those points, I can see I am looking at this point and this point. So basically, if I want to write the equation of a line, what kind of information do I need? So to write an equation of a line, I need, well, I could do it with a point and a slope, or I could do it with 2 points. So if I have 2 points on my line, I can write the equation of that line. And so what I'm going to do is I'm going to compute my slope first of all. And so I'm going to do the change in y over the change in x. And so that's going to be, well, okay, I need to find those y values actually. So if I'm at the x value 2, what is the y value that goes with that? Let's see here. So I'll have negative 1/2 2 minus 2 squared plus 1, so that's just 1. So 2, 1 is that point. And this point is 4 comma, let's see what it is, negative 1/2 4 minus 2 squared plus 1, so that's negative 1/2. So 4 minus 2 is 2 squared, so that's negative 1/2 times 4 plus 1, so that's makes negative 2 plus 1 is negative 1. All right, so those are my 2 points. So the change in y is going to be negative 1 minus 1 over, and then I'll have 4 minus 2. So I get negative 2 over 2, so my slope is negative 1. So it makes sense to have a negative slope there. Yeah, if I move from left to right, my line is decreasing, so negative slope makes sense. So then I want to write down the equation of that line. So if I use point slope form, y minus y1 equals m times x minus x1, which is really just a rearrangement of the slope formula. I can plug in one of my points and the slope that I have here. So I can do y minus, and for my y1, I'm going to use this guy. And so for y1, I'm going to use 1 equals, my slope is negative 1, and then I'll have x minus, and then for my x1, I'm going to use this dude, which is 2. And so that is my equation there of my line. So I'm done. Boop. So I'm not sure, your instructor may want you to solve that for y or something, but anyway, it doesn't say, so I'm just going to leave it like that. And then it says, find an equation of a line that passes through a point, negative 7, 1, and is perpendicular to this line. So the first thing I want to do is I want to find the slope of this line, of that guy. And so if I do that, I have negative 2y is equal to, let's write 5x plus 6. If I add that 5x over, and then I can divide by negative 2. So I get negative 5 halves x minus 3. Yeah. And so this is the slope of the line, but I want to find the slope that's perpendicular. So to find the slope that's perpendicular, I've got this little imperp, is going to be the negative reciprocal of that one. So it's going to be positive 2/5 is going to be my new slope. And again, I can use the point slope form. So y minus y1 equals m times x minus x1. And so I can let this guy be my x1 and this guy be my y1. And I'm going to use this new slope that's perpendicular. And so I'll have y minus 1 is equal to 2/5 x minus -7, so x plus 7. Okay. And again, there's that equation of the line. So you could rearrange that if you wanted to write it in slope-intercept form. Okay. This one says, for a salesman, the profit when 10 vacuum cleaners are sold is $462, and the profit when 25 vacuums are sold is $1,422. We can assume, so we are told to assume this is a linear relationship, and I want to find the average rate of change in the profit for each vacuum sold. So to find the average rate of change of profit, I'm going to do change in profit over change in the number of vacuums sold. So if I want to do the change in profit, it looks like as I sell more vacuums, my profit goes up, so I should expect a positive rate of change here. So we'll do 1,422 minus 462 over 25 minus 10. So if I do that, I get 64. And the units of that are dollars on top per vacuum. Okay. Yes. So then I want to write a linear function for profit as a function of the number of vacuums. And so again, I'm going to use this point slope form. I have y minus y1 equals m times x minus x1. But here I don't have x1 and y1. I have p and n. So I'm going to have p minus p1 equals the rate of change, n minus n1. So that's what I want to use here. So let's see. So I'm going to just pick one of these to be my N1, and this is going to be my P1, and I'm going to use that in my formula. So I'll have P minus 462 is equal to my slope, which is 64, and then N minus N1, which is 10. And so that's my linear function for the number of vacuums. So I can stop there. Or maybe we'll go ahead and reduce that a little bit. So I get P is equal to, let's see, 64 times N. So multiply that 64 into both of those. So I'll have 64N minus 640. And I can add that 462 over. So I end up getting P is equal to 64N minus 178.